Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on module Radiation Detectors Part 7 under the paper Nuclear and Particle Physics. After completing this module, the students will be able to have number 1, knowledge of basics of scintillation detectors, number 2, essential components of scintillation detector system, number 3, types of scintillation detectors and their properties. Scintillation detector. Detection of radiation by light produced in material upon their interaction. So scintillation detectors basically how they detect is when radiation comes, enter in the detector, it basically produces light. How does it produce light? That it excites, the incoming photon is basically absorbed by the molecule of the detector material, and then molecules get excited, and when they de-excite, light is produced. So this scintillation detection method is the oldest method available for detection or spectroscopy of a range of detectors. Essential components. What are the essential components of these kind of detectors? Is that the important component is scintillator. Scintillator means the materials which produce light. Another important component of scintillation detectors is photomultiplier tube, which is usually called as PMT. Photomultiplier tube is the one basically which absorbs the light, emits it and multiplies it. Multiply the number of electrons to make the sufficiently high output pulse. So photomultiplier tube basically absorbs light and releases photoelectrons. Then we have the signal processing unit. Signal processing unit means whatever output pulse we have got at the end of the detector, then that output pulse need to be processed to get some useful information from it. So we need some signal processing units to do that. So it means we need electronics to see the response of radiation. Process. What is the process in scintillation detector that lead to the detection of radiation in the form of an output pulse? Radiation interacts with detector, visible light is emitted. Means when the radiation enters in the detector, it interacts with the molecules of the material of the detector, and then molecules are excited. When they de-excite, then they produce photons of wavelength which fall in the visible region. So we can say that when they de-excite, the light is produced. The light strikes a photocathode and photoelectrons are emitted. So this photoscintillator material is basically optically connected to a photocathode. So this light is absorbed by the photocathode which produces electrons. Photoelectrons are accelerated and multiplied in PMT and signal is produced. So these photoelectrons then basically enter in the photomultiplier tube, and then where various diodes are placed at various increasing potential, and in that way we get sufficiently large number of electrons at the end of the PMT, which then gets converted into a net resulting pulse in the output of the detector. Scintillation detectors. A picture is given in which the working of a scintillation detector is basically shown. Now in the scintillation detector, as we can see, the incident radiations are entering, then they are creating light. That light basically is falling on photocathode, electrons are getting generated, then they are basically guided towards diodes where secondary electrons are getting generated, and then finally all the electrons are getting collected at the anode and then some pulse is generated. That pulse is basically fed to the preamplifier and then to the amplifier, and then after the amplifier the output is fed into the MCA, and then finally the data goes into the data storage system. So this is the working of a normal scintillation detectors. Scintillation detector, scintillator. Now in this slide we will look into the components of a scintillation detector. The important part of scintillation detector is the scintillator. Scintillator is nothing but the crystal in which the radiation interact and emit photons, light photons, or light is emitted. A scintillator is an inorganic or organic material which produces light via fluorescence and phosphorescence process on interaction with radiation. So the light is emitted through various processes in the scintillator like fluorescence and phosphorescence. An ideal scintillator material should have the following properties. What are those properties? That it should efficiently convert energy of radiation into detectable light. It means the material should be such so that when the radiation interact, it is capable of reporting or responding to each such interaction. Second property is conversion should be linear, that is light yield proportional to the deposited energy. That is, the material, scintillator material should be such so that for different energy radiations, different amount of light should be produced. Another important property the material should has, the material should be transparent to the wavelength of its own emission. It should not happen that when the radiation interacts, the molecule of the material is excited, and when it de-excites, it emits the radiation. So material should not absorb its own emitted light. So the material should be transparent to the wavelength of its own emission. Next important property is the decay time of excited states should be short, fast signal pulses. That is, the material should be such so that when radiation interacts with the material, excites the molecules of the medium, then medium should basically, the molecule should immediately release light and come to their ground state, because how fast the light is emitted basically gives the timing of the signal pulses. Another important property the material should has is that the material should be of good optical quality, rugged, unaffected by moisture, and inexpensive. So in this slide, we are discussing the scintillation detectors. So as we have seen that the first important component or first important part of the scintillation detector is the scintillator. In this slide, we are going to study what type of scintillator materials we have. There are two types of scintillator materials we have. Scintillator material means which produce light with the interaction of radiation. So there are two types of scintillator materials which are used for the radiation detection. First category is the inorganic scintillator. Inorganic scintillator means alkyl halides like sodium iodide, cesium iodide, barium fluoride, etc. These inorganic scintillators have best light output and linearity, but are relatively slow in response. Another important property of inorganic scintillators is that they are mostly used for detecting gamma rays due to their high Z and high density. Another category of scintillator materials is organic scintillator. Organic scintillators are nothing like, examples are like anthracene, plastic, etc. These organic scintillators are usually preferred for beta spectroscopy and fast neutron detection because they are fast in response as compared to inorganic scintillators. The process of light emission in scintillator is basically uh, fluorescence. Fluorescence means prompt emission of visible light. Another important process of light emission is delayed fluorescence, which what is delayed fluorescence? Fluorescence, but with a much longer emission time. And the third important mechanism by which the light is produced by scintillators is phosphorescence. Phosphorescence means delayed emission of longer wavelength than fluorescence. So these are the three mechanisms by which light is produced in the scintillator material. Organic scintillator. Now here in this slide, two pictures are shown in which the energy level diagram of an organic scintillator is shown. So in the left hand side picture, energy level diagram of organic scintillator is there, where the energy levels are classified as S0, S1, S2, S3. Then radiation is interacting and the molecules of organic scintillator are getting excited to various energy levels, and then after the de-excitation, first of all the excited level like S3 is coming down to S1 state through radiationless interaction, that is through the collision. Then S1 state is basically decaying into T1 state, and then T1 state is decaying to the ground state by phosphorescence process. When S1 state is decaying to the ground state, then the process is fluorescence. So we can say that there are different ways by which the de-excitation of excited molecules is happening. Some de-excitation is through fluorescence process, some de-excitation is through phosphorescence process. The energy difference is also being shown. Now in the picture on the right hand side, we can say that it's a picture showing the absorption or emission intensity of organic scintillator as a function of wavelength. So in this case, absorption wavelengths are different than emission wavelength. So this is a perfect condition when the material should show this kind of property. Otherwise, if they overlap, then absorption and emission, then the absorption of self-absorption of the light will happen in the crystal. So the picture shown is basically for a good quality organic scintillator where the absorption wavelengths are different than emission wavelengths. In organic scintillator, light is emitted, that is fluorescence, from transition in the energy levels of single molecule. We have seen that if we draw the energy levels of single molecule, then the excitation and de-excitation process basically excitation of the molecule takes place. De-excitation process happens in a number of ways. The prompt fluorescence intensity at a time t following excitation is given by I is equal to I naught exponential minus t over tau, where tau is equal to decay time of S10, that is around few nanosecond. So we have seen that when the molecule of the detector medium de-excites, then it de-excites through fluorescence as well as phosphorescence. The fluorescence are basically prompt, and the intensity of light obtained through fluorescence process is basically having the behavior I is equal to I naught exponential minus t over tau. Lifetime of the first triplet state, that is T1, is around few milliseconds, is characteristically much longer than that of the singlet S1 state. So it means, as we know that in the single molecule, in the excitation levels of single molecules, that the de-excitation takes place through the singlet levels as well as through the triplet levels. The singlet levels, basically the de-excitation through singlet levels gives the fluorescence component, and the de-excitation through triplet states gives the phosphorescence. Now Here in this slide, basically we have seen that the prompt fluorescence has the lifetime of the order of few nanoseconds, whereas the phosphorescence has a lifetime of order around few milliseconds. So we can say that fluorescence is basically prompt and phosphorescence is bit delayed. While in T1 state, some molecules may be thermally excited back to S1 state and consequently decay as normal fluorescence. So when the molecules are in the T1 state, then some of the molecules due to collision or other process may be thermally excited back to the S1 state. Those molecules will also de-excite through the singlet state, that is through the fluorescence process, but those fluorescence are called delayed fluorescence. So it means when the radiations interact with organic scintillators, then the molecule of the organic scintillator get excited, de-excites through three different ways: prompt fluorescence, phosphorescence and delayed fluorescence. These three components of light emission basically have different lifetimes. Prompt fluorescence has the lifetime of the order of few nanoseconds. Phosphorescence has the lifetime of the order of few milliseconds, and delayed fluorescence is further delayed. Organic scintillators are generally used to detect electron and positrons, alpha particles and fast neutrons. For gamma rays, they have no photoelectric cross section, so no photo peak is obtained and only Compton continuum is obtained. Basically, we see two pictures. The picture on the left hand side shows the behavior of light output as a function of time. So here you can see that all three components are being shown. Basically, two components are shown, the delayed ones and the fast component. Fast means the fast fluorescence component and delayed means either phosphorescence or delayed fluorescence. So we can see that the fast component has the exponential behavior with time, whereas the delayed component is basically an inclined line. The sum of these two at any given time is basically the total light output, and it also has the exponential character as a function of time. So overall shape of the pulse is given by n is equal to a exponential minus t over tf plus b exponential minus t over ts, where tf is the fast component and ts is the slow component, and a and b are the constants. Ratio of a and b varies with the material, but fast component always dominates. It means basically the light which is emitted in the prompt fluorescence is the main light which dictate the terms. Now in this case, in the picture on the right hand side, the typical energy spectrum for neutron detection is given. The spectrum is plotted between counts versus neutron time of flight, and here you can see that the energy peaks corresponding to gamma rays and neutrons are clearly separated. Organic scintillators. In this slide, we are going to study or we are going to discuss the limitations of organic scintillators. Up to the previous slides, we have discussed various properties of organic scintillators and how they produce light. But in this particular slide, we are going to study their limitations. The first important limitation of organic scintillator is the time response can be their time response can be affected or worsened due to either varying flight time of photons to the PMT or due to the self-absorption or re-emission of fluorescence by the scintillator itself. Another important limitation is surface of plastic scintillators can become crazed on exposure to extreme environment, which leads to substantial drop in light output from large scintillation because of the decreased efficiency of internal light reflection. Another important limitation is the prolonged exposure of organic scintillator to ionizing radiations lead to deterioration of their properties. Inorganic scintillator. In this slide, we are going to study the various properties about the inorganic scintillators. Insulating crystals with large band gap like sodium iodide, cesium iodide, doped with activators like thallium or cerium to create impurity levels within the band gap. So they are inorganic scintillator means they are the inorganic molecules like sodium iodide and cesium iodide, and in these pure inorganic molecules some impurities which we call as activators are basically added. The impurity added is most commonly of thallium or cerium. These impurities basically create the energy levels in the band gap for pure sodium iodide or cesium iodide crystals, and they are called, these energy states are called activator sites. Their scintillation mechanism depends on the energy state of the material. That is, the scintillation mechanism in inorganic scintillator depends upon the energy states of crystal. Activator added in a small amount to enhance probability of photon emission. And here in the bottom of this slide, two pictures are shown. And the picture on the left hand side indicates the positioning of the energy levels, where the valence band is shown, conduction band is shown. These valence and conduction bands are corresponding to, or these valence and conduction bands are for pure crystals like sodium iodide or cesium iodide. Then there are, in between them, there are few energy states which are given as activator sites. These energy states are corresponding to the activator or the impurity like thallium or cerium, and then activator excited states are there, ground state is there, and on the right hand side picture we can see that the photons are coming, they are getting excited, then through some process they are de-exciting to impurity level, impurity excited states, then again impurity excited states decay to impurity ground state by releasing a photon of energy 440 nanometer, and then impurity ground state then finally decays through collision or other non-radiative process to the ground state of inorganic crystal. Inorganic scintillator. So up to the previous slide, we have basically discussed the organic scintillator kind of scintillator materials and their properties, their limitation. But now in this slide, we are going to study the inorganic scintillators. In the inorganic scintillators, activators make a special site in lattice and create energy states in forbidden gap through which the electron can de-excite back to the valence band. So this is an important mechanism in inorganic scintillators. The transition rate between the transition between the activator excited states and activator ground state gives rise to a visible photon and serves the basis of scintillation process. So now the process, that how the light is emitted in the inorganic scintillator. Charged particles enter in the medium and creates electron hole pair. So charged particles enters in the medium and create electron ion pairs, electron hole pairs. Holes quickly drift to the activator and lose it, their ionizing energy is less. Electrons migrate in crystal until they find an ionized activator site and neutralize it. The neutral configuration has its own excited energy state. Then, if the activator excited state has an allowed transition to the ground state, it de-excites. Its de-excitation occurs very quickly, that is tau around, within the time frame of tau around 50 to 500 nanosecond, and photon is emitted. For most scintillators, it takes about 3 times the band gap energy. For example, in sodium iodide, it's around 20 electron volt to create one electron hole pair. To make full use of scintillation light, the spectrum should fall near the wavelength of maximum sensitivity of the device used to detect the light. Scintillation detector, photomultiplier tube. Now in the scintillation detector, another important component is the photomultiplier tube. As the name suggests, this part basically is responsible for the multiplication of charge carriers. It essentially has the diodes which multiply the electrons. A device doing charge amplification and producing output pulse proportional to number of original photoelectrons is the photomultiplier tube. What are the components of this photomultiplier tube? It consists of photocathode material. Photocathode material means the material which emits electron when the light interact with the material. Then we have diodes. Diodes means electrodes giving additional electrons after being struck by electron. Multiple diodes result in around 10 to the power 6 or more number of electrons. Then we have collector. Collector is nothing but the anode. It accumulates all the electrons. And then finally we have the resistor, that the collected current passes through resistor to generate output pulse. And these components are clearly marked in the picture on the right hand side of this slide. Scintillation detector limitations. Now in this slide, basically we will look into what are the limitations of scintillation detector. Now important limitation of scintillators is their relatively poor energy resolution. So scintillator detectors are basically poor in energy resolution. Second limitation is process of converting radiation energy to light, and then an electrical signal involves many inefficient steps. So energy required to produce a photoelectron is high, that is around 100 electron volt, and the consequence of this is that number of charge carriers created few thousands. So this is very important limitation, that in this case when the light is emitted by the scintillators, then only this light is basically only limited portion of this light is used to create electrons. So we can say that, and the energy required to produce a photoelectron using this light is around 100 electron volt, which is high, and as a result number of carriers created few thousand. Since less number of charges are created, so energy resolution basically is poor. Now sodium iodide type of scintillator detector is more hygroscopic and fragile. So we can see that the sodium iodide thallium scintillator is basically more hygroscopic. Hygroscopic means it absorbs water very fast. So if we are working in a condition where the moisture level is high, then the moisture level can damage the sodium iodide scintillators. Also these detectors are fragile, they are prone to destruction. Cesium iodide detector, thallium scintillators, less hygroscopic and fragile than sodium iodide. PGO scintillators, low light yield, around 10 to 20% of sodium iodide, high refractive index, so light collection is difficult, more expensive and less hygroscopic. So students, let us summarize what we have learned in this module. There are very many concepts which basically we have gone through, and now it's time for us to recap what we have learned. The first important thing we learned is that scintillation detectors detect radiation by producing light on their interaction. Second important thing that we have learned is, depending upon the type of material used to produce light, scintillation detectors can be inorganic or organic type. Third important thing is, in scintillation detectors, The process of light emission involves fluorescence, delayed fluorescence, and phosphorescence. Another important thing we have understood is that in the light emission process, the activators and their concentration in the scintillation material plays an important role. They are hygroscopic, fragile, poor energy resolution, but with high efficiency. Thank you very much.